All right, let's do a deep dive into NumPy. If you've ever found yourself just battling with array dimensions or getting those cryptic value errors, then you are in exactly the right place. We're going to go way beyond just using NumPy and really get into its core mechanics. The goal? To turn those common frustrations into some seriously elegant, high-performance code.
Yeah, I'm pretty sure we have all been here, right? Staring at this exact error message, just scratching our heads. It's got to be one of the most common hurdles in NumPy. But what if I told you that by the time we're done here, you won't just know why it happens. You'll have this solid mental model to stop it from ever catching you by surprise again.
So here's our game plan. We'll kick things off with the basic anatomy of an array, then jump into the powerful mechanics of reshaping and broadcasting. We're going to uncover a really critical warning about views versus copies. Trust me, this can save you from some really tough-to-find bugs. And to wrap it all up, we'll peek under the hood and see how memory layout is the secret sauce to NumPy's incredible speed. Let's get into it.
Okay, before we can start bending data to our will, we really need to understand its building blocks. Think of it like a mechanic needing to know every part of an engine before they can even think about tuning it for performance. These basic properties, shape, size, and dimensions, they're the blueprint for every single thing we're about to do.
The shape is probably the most important attribute you'll ever deal with in NumPy. And this shipping container analogy, it's perfect. A one-dimensional array is like a single row of boxes. Its shape is just length, comma. A two-dimensional array is more like a grid, right? Boxes stacked in rows and columns. That gives it a shape like rows, columns. And a 3D array, well, that's our cube, with a shape of depth, rows, columns. This little tuple, the shape, is basically our map to the entire structure of the data.
Now here's the really elegant part. Look at how these three attributes are all tied together. The number of dimensions, .ndim, that's just the length of the .shape tuple. So for our 2, 3 example, the length is 2. Simple. And the total number of elements, .size, is just what you get when you multiply the numbers in that shape tuple. So what's the size here? 2 times 3, which is 6. See? They all describe the exact same structure, just from slightly different points of view.
Okay, so now that we've got a solid grip on an array's anatomy, let's actually put that knowledge to work. The first powerful tool we're going to look at is reshape, and you'll see immediately how it builds directly on what we just learned about shape and size.
This is it. This is the golden rule of reshaping, and it is the direct cause of that value error we saw at the very beginning. You cannot create data or destroy data using reshape. All you're doing is changing the container that it's in. An array with 12 elements can be a 1 by 12, a 2 by 6, a 3 by 4, whatever, but it can never ever be a 3 by 3 array. Why? Because that would need 9 elements. The .size absolutely has to stay the same.
So let's see this in action. If we run np.arrange12, we get a simple 1D array with 12 elements, numbered 0 to 11. Then we can call .reshape34 on it. And why does this work perfectly? Because 3 times 4 equals 12. The total number of elements is preserved. The data itself, the numbers 0 through 11, haven't changed at all. Only our perspective on how they're arranged has.
Okay, this next one is a huge time saver, and honestly, a sign of really clean NumPy code. Instead of doing the math in your head, okay, I have 24 elements, I want 4 rows, so that means I need 6 columns, you can just tell NumPy, hey, I want 4 rows, you figure out the rest. And you do that by using -1. This is so powerful in machine learning, where maybe your batch size changes but your number of features is fixed. You just reshape with -1, n features, and let NumPy do all the work for you.
Now we need to cover a really critical detail about reshape. If you misunderstand this, it can lead to some incredibly subtle and frustrating bugs. It all comes down to what reshape actually gives you back. Is it a view or is it a copy?
This is a massive gotcha for a lot of developers. So reshape is super fast because whenever it can, it doesn't actually copy any data. It just creates a new view. Think of it as a new set of directions that points to the exact same block of memory. On the other hand, a method like flatten will always give you a brand new, completely independent copy of the data. The trade-off is pretty clear. Reshape is great for memory and speed, but flatten is safer if you absolutely have to make sure your original data doesn't change.
Okay, watch this closely. We make an array, we reshape it, and then we change the very first element of the reshaped array to 99. But when we print the original array, we see that it has changed too. Why? Because both variables, original and reshaped, are just pointing to the same underlying data in memory. A change made through one is visible through the other.
But now, look at the difference with flatten. We do the exact same thing, create an array, flatten it, change the first element of the new array. This time, when we print the original, it's completely untouched. That's because flatten created a whole separate copy in a new spot in memory. This is the safe route when you need to protect your source data. But remember, it costs you a bit more memory and time.
So, we've figured out how to change the shape of one array, but what happens when we try to do math between two arrays that don't have the same shape? This is where one of NumPy's most powerful and honestly kind of magical features comes into play. It's called broadcasting.
I bet you've used broadcasting 1,000 times without even realizing it. Anytime you take a whole array of, say, distances in miles and multiply it by a single number, like 1.6, that's broadcasting. NumPy is smart enough to see that you're combining a big array with one little value, and it just applies that operation to every single element for you. That is broadcasting in its simplest form. This idea of stretching is the key to getting broadcasting. But the key word here is conceptually. NumPy is way too smart to waste memory by actually creating a giant new array. Instead, it just reuses the smaller array's data over and over again during the calculation, which makes the whole thing incredibly efficient. It's a powerful way to let optimized C code do the looping for you instead of slow Python code.
So how does NumPy decide if two arrays can be broadcast? Well, it's not magic. It follows a very strict set of rules. First, it lines up the shapes of the two arrays from the right side. Then, moving from right to left, it compares the dimensions. Now, for each pair of dimensions, the broadcast can happen if they are equal or if one of them is 1. If one is 1, it gets stretched to match the other. If at any point that rule isn't met, the whole thing fails with a value error. All right, for our final section, we're going to peel back the very last layer of abstraction. We are going deep under the hood, into the computer's memory itself, to understand the fundamental reason why NumPy is just so fast, and why things like reshaping and broadcasting are so optimized. This is where the real magic happens.
You know, the way your data is physically laid out in memory has a massive impact on performance. C order, which is the default in NumPy and a lot of other languages, stores data row by row. So the elements 00, 01, and 02 are literally right next to each other in memory. F order, which you see in languages like Fortran, is the opposite. It stores things column by column. So 00, 10, and 20 would be neighbors. Think of C order as reading a book left to right, and F order as reading down a newspaper column.
This brings us to this idea of strides. An array's strides attribute is basically a low-level treasure map. It tells NumPy exactly how many bytes it needs to jump in that flat block of memory to get to the next element in each direction. So in a C-order array, the stride for going across the columns is going to be small because the next element is right there. But the stride for going down to the next row will be big because you have to jump over a whole row's worth of data to get there.
And this slide right here shows us exactly why this all matters so much. Think of your computer's main memory, your RAM, as a giant library. And think of the CPU cache as your desk. It is way faster to work with books you already have on your desk than to keep running back to the library for every new piece of information. When data is contiguous, meaning small strides, the CPU can grab a whole chunk of it, a cache block, and put it on its desk. This means the next operation will probably find the data it needs right there, in that super fast cache. With large strides, the CPU has to keep making slow trips back to the library, and your code just grinds to a halt. This is the secret to NumPy's performance.
All right, let's bring it all home and go over the key things we've learned on our journey, from a simple error message all the way down to the hardware.
We've covered a ton of ground. You now get that an array's shape, ndim, and size are all part of one system. You know the golden rule of reshaping. The size can't change. You know how to use the -1 trick like a pro. You get the critical difference between a fast, memory-efficient view and a safe copy. You can actually predict how broadcasting will work. And maybe most importantly, you now see that memory layout and strides are the keys to unlocking NumPy's real speed. You're now set up to write faster, cleaner, and way more robust NumPy code.
So this isn't just theory, right? The next time you're building a data pipeline, I want you to ask yourself, how is my data actually laid out in memory right now? Are my operations keeping it all together, or am I accidentally fragmenting everything and slowing it down? Thinking about memory layout from the start can be the difference between a good solution and a truly great one. Thanks for watching.